More than 5,000 extrasolar planets found. But what have we learned? Billions of stars, red, yellow, orange, blue, and white, shine in space at distances measured in millions of billions of kilometers, thousands of times farther than the most distant planet in our solar system. There's no doubt that since the beginning of conscious thought, mankind has sought to understand the universe. Today, astronomers armed with evidence of the existence of planets around other stars are asking more specifically, what are these planets like? Of the 100 billion stars in our galaxy, the Milky Way, how many host planets? And among those planets, how many are just dry deserts or icy spheres of hydrogen? Are any of them home to lush forests or oceans teeming with life? Today, for the first time in history, astronomers can begin to answer these questions. It was in 1995 that two astronomers, Michael Mayer and Didier Queloz, discovered the first extrasolar planet, 51 Pegasi b, around the star 51 Pegasi, a giant gas planet with Jupiter-like dimensions orbiting a sun-like star. To date, more than 5,000 exoplanets have been discovered, and the number continues to grow. The refinement of observational methods and the development of dedicated spacecraft missions to make the search for exoplanets, especially those that might have favorable conditions for harboring life, one of the most exciting topics in astronomy. But how do we detect these planets? What is their composition? What instruments and spacecraft missions are planned for the coming decades? And finally, will it be possible to find other habitable planets? The purpose of this video is to answer some of these questions, but mostly to invite you to reflect on the incredible and mysterious beauty that surrounds us. As of May 24, 2023, there are 5,382 confirmed exoplanets in 3,974 planetary systems, with 858 systems having more than one planet. Most of them have been discovered by the space telescopes Kepler, active from 2009 to 2018, and TESS, active since 2018, not to mention the European Cheops, active since 2019. However, there are 9,618 more in the archives waiting to be confirmed. So very soon, even in the unlikely event that new discoveries cease, the total number of extrasolar planets already identified could rise to nearly 15,000. Not bad, right? In less than 30 years, a lot has happened since that day in 1995, and it seems that the future will bring us even better prospects, although the road will become more and more arduous as the distances we have to explore increase. Indeed, the search for extrasolar planets is hampered by objective perpetual difficulties. It is in fact a matter of comparing a very small and dimly lit body, the planet, with a very large and very bright one, the star. A bit like identifying from a distance of several kilometers a moth circling the light of a street lamp. The star appears, on average, 1 billion times brighter than the nearby planet, so that the latter is invisible because it is bathed in a blinding light. However, if the observation were made in the infrared instead of the visible, it would be found that the difference in brightness between the two bodies is only 10,000 times, a value which is still very high, but which in the best cases would allow the planet to be distinguished from the star. In addition, the two celestial bodies are often so close together that even the resolution of the largest terrestrial telescopes cannot separate them. For example, a planet like Jupiter at a distance of 10 parsecs, about 32 light-years, would appear to be separated from the Sun by only half an arcsecond, practically in close contact with the star and barely distinguishable from it, and 10 parsecs is a minimal distance in the vast cosmic space. Finally, if the ratio of the mass of the central star to that of a planet like Jupiter is about 1,000, it is more than 300,000 compared to Earth, and therefore the gravitational perturbations that a planet like ours would exert on an average-sized star would be insignificant. This is also the reason why only planets of considerable size and very close to the star they orbit have been discovered so far. So how do astronomers discover new exoplanets? Well, there are mainly indirect and direct methods. Until the 1990s, the solar system was the only existing model of a planetary system. We did not even know for sure if planets were orbiting other stars. so we could not know in what mass and size combinations these unknown planets were orbiting their stars. But starting in the second half of the 1990s, everything changed. With the advent of digital technology and the improvement of optical technology, in a little more than 2 decades, we accumulated firm evidence of the existence of thousands of exoplanets, thanks mainly to 2 methods: the measurement of the radial velocity of stars, the measurement of the micro variations in brightness that indicate the transit of planets in front of the stellar disk. This has resulted in the creation of a large database of planetary objects, an astronomical zoo populated by different types of planets, some of which do not exist in the solar system, such as super-Earths and hot Jovian planets. Super-Earths are exoplanets with a mass of 2 to 10 times that of the Earth and are thought to be rocky like our planet. So far, 1,650 have been cataloged with these characteristics. Hot Jovians, on the other hand, are gas giants, hypothetically similar to Jupiter, but orbiting very close to their stars in a hellish dance that was not thought possible because planetary formation theories suggest that Jupiter-sized planets can only form far from their stars, beyond the so-called ice line, i.e. where the temperature is so low that water can only exist in icy form. At the lower end of the scale are Earth-like worlds, bodies that contain silicates and water in varying proportions, but do not have an extended envelope of volatile elements. May have an atmosphere, but is relatively thin, and there is always a solid surface beneath it. True rocky planets belong to this category. Their radius is less than 1.25 times that of Earth, and their mass is between 0.1 and 2 times that of Earth. So far, 198 have been found. The next category is the Neptunian worlds. The solar and extrasolar planets that belong to this category differ from Earth-like planets because they retain large atmospheres of helium and hydrogen due to their greater gravity. Even if they had a solid surface, the vast gaseous layer covering it, extending for thousands of kilometers, would create unbearable pressure for any form of life. With its 95 Earth masses and very low density, Saturn is at the upper limit of the Neptunian world category. To date, 1,859 have been discovered and confirmed. The third category is that of the Jovian worlds, gas giants, composed mainly of helium and/or hydrogen. These planets, like Jupiter and Saturn in our solar system, have no hard surfaces, but instead have swirling gas over a solid core. Gas giant exoplanets can be much larger than Jupiter and much closer to their stars than anything found in our solar system. We have discovered 1,707 of them so far. Is there anything anomalous about our solar system? Or do we still know too little about extrasolar planets to hope to classify them properly? Perhaps both, but the latter is certainly more likely. Let's see why. To understand the nature of an exoplanet, i.e. whether it is rocky or gaseous, 2 essential pieces of information are needed: mass and radius. For example, the Earth, a rocky planet, has a density of 5.5 grams per centimeter cubed. Saturn, a gaseous planet with no solid surface, has a density of only 0.7 grams per centimeter cubed. Between these 2 extremes lie all the bodies of the solar system, moons, planets, and asteroids, which are sufficiently massive to have assumed a nearly spherical shape under the action of their own gravity. We know the density of each of them precisely because we know the radius and mass of each of them with equal accuracy. Unfortunately, we don't have the same information about the vast majority of exoplanets. We either know their radius or their mass, but not both. The radial velocity method allows us to calculate the mass of a planet with approximations due to our knowledge of the inclination of the orbit from our point of view, while the transit method provides the radius of a planet. Only in rare cases can we use both methods together, transit and radial velocity, and obtain precise knowledge of both the radius and the mass. In all other cases, when we only know one of the 2 elements, the determination of the type of planet is purely speculative, although based on reasonable assumptions. However, the continuous improvement in instrument sensitivity is providing new methods to characterize the discovered planets. For example, in the case of planets that eclipse their star, spectroscopy allows us, in some cases, to observe a difference in the system's spectrum, which is the sum of the stars and the planet's spectra, when the planet is hidden by the star and when it passes in front of the stellar disk. This difference can be attributed solely to the planet and therefore provides information about the chemical composition and temperature of its atmosphere. Similarly, the variations in infrared radiation from the system during the planet's revolution around the star provide information about the different surface temperatures of its regions, depending on the illumination, day-night alteration, thus allowing us to infer its surface temperature and the presence of an atmosphere. The continuous refinement of these measurement techniques may one day provide us with clues about the positive existence of life forms. For example, geologists assure us that the abundance of oxygen in the atmosphere is a fairly certain symptom of the presence of life. In fact, oxygen is an extremely reactive gas that easily combines with other elements to form oxides and anhydrides. The Earth's atmosphere would lose all of its oxygen within a few million years if it were not for plants that continuously produce it by decomposing carbon dioxide. Therefore, the discovery of oxygen in the atmosphere of an extrasolar planet would be a good indication of the presence of life on it. Yes, the same old talk about the search for life. It is an obsession we will never get rid of, in the hope of one day being able to look into the eyes of creatures similar to ourselves, but also because of the legitimate desire to discover habitable planets for the future of our species. To find an Earth-like planet that is ideal for us and life, astronomers must look for planets that are neither too cold nor too hot and temperate enough to have water, which is the mixer and solvent of organic chemistry and biochemistry. Planets with the perfect combination of molecular ingredients orbiting their sun at just the right distance enjoy what astronomers call a Goldilocks orbit. If we saw such a planet, an endless stream of questions would arise. Does its atmosphere contain oxygen, nitrogen, and carbon dioxide like Earth's, or sulfuric acid and CO2, the deadly mixture of Venus? Is there a protective ozone layer, or is the surface scorched by harmful ultraviolet rays? Even if a planet has oceans, will the pH of the water be neutral enough for cells to grow? Besides, even if primitive life had blossomed on another Earth, is it certain that it would always culminate in intelligent life forms? Or is human technology just a stroke of Darwinian luck? Are we a rare work of nature destined to appear only once in an Earth-like planet in a universe otherwise teeming with primitive life? It may seem surprising, but some of these questions are likely to be answered in our lifetimes. With the help of instruments already in existence, such as the Webb telescope, or in the planning stages, such as the European 39-meter telescope under construction in Chile's Atacama Desert, it's hard to imagine what we'll discover by the end of this decade. Yes, because the destiny of our species is to explore the galaxy and find its biological and chemical roots out there among the stars.